Well, the idea behind it, well, what you do for a direction field is you're just picking several points in your ty plane. And so, for instance, something like this. So we're picking t equals 1, 2, 3, and so forth. Y equals so on. Actually, for this particular problem, because of the DE involves cosine t, it'd be a good idea to pick t values that are like pi over 2, pi. You can pick convenient values like that. Also, it doesn't really matter; it's your choice. And the idea is, at each of these points, the arrows that you're drawing, each one, so if I identify this point as t naught, y naught, so the slope of this arrow should be equal to the value of y prime, which is f. So whatever y prime is equal to, evaluated at that. Whoa, that was extremely uncomfortable. Okay. Y prime evaluated at that point, and of course you should draw the arrows in a way that they don't overlap each other, so make them pretty short. But and what the problem is asking about is, as you start to do these, are there certain trends that you can see based on the slope? And as I mentioned to someone else who asked me about this same problem, it might not be a bad idea to actually do the other parts of a problem first to get an idea as to, like, if it's looking for its critical value, A naught, because that gives you an idea as which y values to focus on, so that you can see, okay, here's where there's an identifiable change of behavior. Because there's some differential equations that we'll see later where at around some y value, you may see very different behavior on one side than what you see on the other. Like here, tending toward this line, turning away from it. These are the kind of things that can happen. So the idea is to get a feel for that in this equation, that different behavior can ensue. Admittedly tedious, and that's one reason why I suggested picking convenient values to plug into the function. Any other homework questions? You were asking about 28?
Honestly, don't know. Like, aside from like the basics, like figuring out what is my P, what is my Q.
Yeah.
I didn't know what to do with 28.
Okay. Well, 28 has a few items to it. So, are you talking about just being able to solve the differential equation itself?
Yeah.
Okay. Because all of the differential equations is assignment. But the idea is to get, if they're not already in this form, to get it in this form. And I guess and you were able to get that far as identifying what is your P, what is your Q.
Yeah.
So okay. But that is, well, in that case, what you can do is, well, really, there's two essential steps here. Your integrating factor, e to the integral of whatever t is. And then once you have that, you have this solution formula. That was derived in class. And you just have to remember, and actually, even though it's not necessary, it doesn't look necessary, I'm going to do it anyway, enclose this in brackets and keep it in brackets. Because when you work out this integral, and by the way, at least some of these problems require integration by parts. like if you have like a power of t times an exponential, something like that. Okay, so you have, so you evaluate this integral, and here I've written it as an indefinite integral. There's going to be a plus c. And remember, that 1 over mu t on the outside is going to multiply the plus c. That's a common mistake, to forget about that. But as far as solving the equation, for everything in this section, that's what you do. Yes?
On 28,
Yeah.
where it asks if you define the solution or the value of y naught, or I guess we call that initial y.
Right, yeah.
Do we just use the initial value solution and solve for the initial value of y? But we don't have, I think I tried to do that and I have another variable.
Okay, because you have, and this, so when I talked about this problem before, you have two conditions. That at this point t star, y has to be 0, y prime has to be 0. So here's one way to do it, is if you were to solve the equation y of t is equal to 0, then you would not get a numerical answer because of non-uniqueness. But then you could get an expression that depends on y naught and substitute that into y prime. And then, so then that way you're enforcing both conditions. But that is not the easiest way to do the problem. Because, and that's why I mentioned, take advantage of all the information you're given. For instance, what does y satisfy? It satisfies a differential equation. So by exploiting that, you can get, that's a faster route to a solution. But basically, you think of it as trying to solve a system of two equations. Okay. In fact, the differential equation is y prime plus 2/3 y is equal to. That's what it was, right? Okay. Since I mentioned the derivative, that gives you a nicer way to get y prime. Your solution already is known to satisfy this, so instead of going through the laborious differentiation, then you can use this to express it. But yeah, 20 in particular is meant to be a doozy for that reason. But I do get partial credit.
And I guess the same way you would solve 28 is how you solve b for 21. I don't know.
I'm sorry, you were saying?
The way you solve 28 is basically the same way you solve part B for 21.
Okay.
But you're asking for A, the initial value of A.
Okay. Sorry. Okay.
What's in the
Well, that should be the hardcover. Copy. Okay. I don't want to go on a limb and say that they're exactly the same, because the conditions you're trying to satisfy are very different. Because what you're looking for in problem 21 is your solution has various terms, certain functions like exponentials that all have coefficients. And what happens to cause a coefficient to become 0, for instance? Because, and I'll give you just a generic example. Suppose y of t is equal to, let's make something up. Okay. Y naught e to the t plus 1 minus y naught e to the minus t. So what you have is, in a general case, what you have is mainly exponential growth. You have exponential growth. Not sure why I switched lowercase, but whatever. And then here, exponential decay. Of course, the exponential growth is going to be dominant. But what initial value could you choose here that would not give you exponential growth? Yeah, so that would wipe this term out. If y naught is equal to 1, then you have only exponential growth and no decay. So this is an example of how a certain initial value can cause a substantial change in the behavior of a solution. Also, of course, if y naught is positive, you'll have exponential growth in the positive direction towards plus infinity. As soon as y naught goes negative, it's going towards minus infinity. So things like that are what we're looking for in 21. Any other? On any problem? Now, because you're not struggling enough with that one, here's another. So this is on a section I just finished on separable and homogeneous equations. Now, the due date tentatively is Monday. I would like to give you a little more time on this one. I'm open to rethinking that. Also, you notice if you've been to the lectures page on the site to watch the videos, you'll see I have homework due dates there. And I basically just tried to fix up as closely to the calendar as I can from the last time I taught this class 4 years ago. And it says there's homework due on the February 6th and on February 8th. I'll work on that. So don't be freaking out.
The first one said it was due.
Yeah, I mentioned that earlier. Yeah, that was a holdover from 4 years ago. And that's another reason why, in case that threw anybody off, because I didn't find out about it until late last night, because that's just the way these things go. To give you, I can be selectively lazy, and what that means is, in this case, in the assignments page, I have all the stuff that's on there from 4 years ago commented out. So when I put out a new assignment after making sure it's okay, because we're dealing with a different edition of a book now than back then, I just uncommented part, slapped it up there. And what happened in homework 1 is, I didn't bother checking to see if the date was what it should be. Whereas when I go into the handout, I'm actually checking my calendar, checking the lecture schedule, intentionally putting in the correct date. In other words, trust the handout. Okay, but I will, now that I'm aware of this, I'll make sure to
What time do you normally
keep both in sync. What?
What time do you normally leave?
Oh, well, actually, I normally am here till like 7 p.m. So it actually gets quiet around here. I don't have ever faculty bugging me. Students don't bug me. It's faculty and staff that drive me crazy. So don't repeat that. But for the purpose of homework due times, if I say, like, okay, the assignment is due any time today, then really, and I know other faculty in the department use the same cutoff, effectively it's due when I walk in here in the morning. So if you if you finish it in the evening and you slide it under my door sometime tonight, then I'll count it as on time. All right. That way there's no ambiguity. Okay. Other questions? Alrighty. Let's go ahead and do the attendance. Now, all right, so unlike the last couple sections, I'm not going to talk about any new techniques for solving equations, but how we use the techniques that we know already, particularly for linear equations, for some application problems. So step outside the math bubble a little bit, which means that today, just today, and maybe Friday too, I'll temporarily care about units. Okay, so that's going to lead off with an example. So in these kind of problems, once the differential equation is and initial condition is obtained, you should know what to do from there, from before. The additional challenge here is how do we set up the initial value problem correctly based on a verbal description. And Visualization helps. Okay, so we have this tank, and what we have is 200 liters initially of a solution that contains some dye. Okay. All right. I'm not going to incorporate the shark into the problem, though. That would make it a little too difficult. So, and the okay. So the initial concentration of the, whoa, that was really bad spelling, dye. I'm going to use the variable Q to refer to concentration of the dye at any time t. That's really what I'm going to solve for. So at the initial time, 0, it's going to be, well, actually, no. Sorry, Q is not concentration. The initial amount of dye. And that amount is expressed in grams. Okay. Now, what we have is the concentration is incorporated into the amount. So we have 1 gram per liter times the volume of our solution, how many liters that we actually have. So since initially we have, all right, so this is an initial condition. Okay, 200 liters, so we just work this out. And paying attention to the units at all times can really help you, give you some confidence that you're really setting things up the right way, because certain units you cancel and so forth. So the amount that we're supposed to get is in grams, and conveniently the liters cancel. So we have, at first, 200 grams of dye in this 200 liter solution. Okay. Now, so what's done with the tank from its initial condition is that we have, water's coming, there's pure water, no dye in it, is coming into the tank to rinse it out. Okay. Now, the inflow from water is 2 liters per minute. So what's happening is water's coming in, and then the solution with dye in it is being emptied out. Okay. And that is also at the rate of 2 liters per minute. So the volume of liquid in the tank is going to remain the same throughout. So water in, water mixed with dye out. Okay. Now, the idea is not necessarily to have the tank completely free of dye, but to try to get most of it out. So the problem to solve here is how long is this rinsing necessary? So in other words, it's a time value that you're looking for until the concentration, so that's grams per liter, is equal to 1% of the initial value. Okay. Now, okay. So what we're solving for, Q, is not a concentration, though, it's an amount. So really we'd like to express this target as an amount of dye rather than a concentration of it. So based on what I've already done here, what should the amount be?
2 grams.
2, yes. Why?
200 liters.
Yes, because the initial concentration is 1 gram per liter. Bless you. We want 1% of that, and also the volume is going to remain constant because we have the same flow rate in of water and outflow of solution. Okay, so so how we arrive at this is 200 grams, 1%. Is 2 grams. So once we find Q of T, then we'll set Q of T equal to 2 grams, and then we'll solve for T. But now what we need is, so our real challenge here is this Q of T, which is the amount of dye at time t satisfy. Okay. So once this done? Yes. Okay. So once we have that, then we can answer the original question. Okay. So to get our ODE, we're going to use this. It's often referred to as like first principles. That flow rate in minus flow rate out. Okay. Okay, so in other words, the amount of substance that's coming in per unit of time, and then we're deducting what's leaving. Now, based on the picture, and for both these, I mean, Q is the amount of dye. So what I mentioned here is flow rate in, flow rate out for dye. So what's the flow rate in? Yeah, it's going to be 0. There is no dye coming in. So it's flow rate out, that'll be the interesting part of this equation. Okay. So what happens is, so here we use the fact that the concentration at time t is equal to whatever amount of dye we have, which is in grams, divided by the total volume of liquid, so solution that's getting more and more diluted in a tank. It's 200 liters. Okay. Now, but the thing is, we have the water's flowing in at 2 liters a minute, and also liquid is leaving at 2 liters per minute. So the outflow so in and out. So in other words, it's really what's going out that's key here. Is so since we have outflow of 2 liters per minute, what we have is, all right, so this is amount leaving per unit of time, and then times the concentration of dye that's in that liquid that's leaving, and that's going to be this, Q of T grams over 200 liters. Okay. Now, since we're using minutes as our unit of time, what are the units of dq dt? What?
Gram per time.
Yeah, in this case, grams per minute. So make sure that what's on both sides of your differential equations have consistent units. So, so grams per unit of time, which is minutes in this problem, because the given information is minutes. And then over here, we're going to have outflow is liters per minute times grams per liter. The liters, those units are going to cancel out. So what we get is grams per minute. So we have 2 over 200, so 0.01 Q of T. So that is your outflow. So now our differential equation is complete. The Q dt is minus 0.01 Q of T, and then our initial condition from before is Q of 0 is 200 grams, because the initial concentration of 1 gram per liter. Okay, so questions about where the outflow of the flow rate out comes from? Okay, so it's just amount of whatever substance is leaving per unit of time multiplied by the concentration. That's it. Okay. And then what's concentration? Amount divided by the total amount of your substance, the total amount of solution. Now, now to prepare you for more interesting problems in this, suppose that the volume is not constant. What if there is a net increase or net decrease? If you can describe as a function of time how the total amount is changing, that still is what would go down here. So even though here it works out conveniently because it's a constant, even if it's not a constant, this is how you get concentration. So amount of your substance divided by the total amount of solution that it's in. Okay. So now we can just go ahead and solve that. Now, since it's fun to ask questions that have non-unique answers, what kind of equation is that in terms of a solution technique? How do we classify it?
Yeah, separable.
It is separable? Does anyone have a different answer?
Does it have a specific name, like it's named after a scientist?
No, more like a generic term. What kind of equations you've been solving on this homework? It's a linear equation. So 0.01 is your P, and Q is 0. So it's because Q is 0 that the equation is not only linear, but also separable. Okay. Now, this fits the generic form y prime is equal to ky, where k is a constant. And I've said more than once that this is something that's good to know off the top of your head, especially for tests. Fill in the blank, somebody. Close. Yes, e to the kt. Okay. So because there's no, in a generic form, little q of t, we don't have to go through the trouble of an integrating factor. You can if you want, but it's not necessary. So in this case, you can jump directly to this. We can apply that to this problem. Okay. All right, so if we apply that to the equation that this equation right here, then what should q of t be equal to? So everything you need to solve this is right here.
200 to the power negative 0.01t.
Yeah. Because this is your q of 0, your initial value, and then the minus 0.01, that is your k. So, so basically, you're just fitting the problem you have to this template that I wrote there, the y prime equals ky, because it fits that. And as we go through the semester, you'll have a few templates like these that you can use to quickly rattle off solutions. Okay, so any questions about how we got that solution? All right. But now we're still the original question. How long will it take for the amount of dye to go down to 1% of the initial concentration? So we had 200 grams at the start. We need to get this down to 2 grams. So, okay. So we need to solve Q of t is equal to 2 grams. So if we go ahead and plug in our solution, e to the minus 0.01 t is equal to 2. So how do we proceed from there?
By 200 and then take a ln of both sides.
Yeah. So e to the minus 0.01 t is equal to 0.01. This happens a lot. That you have an exponential function equal to the percentage that you are aiming for. For instance, radioactive decay, half-life problems tend to work out this way. To figure out half-life, you're setting some exponential equal to 1/2. Okay, so and then you take the natural log of both sides. Natural log and the e cancel out. Those are inverse functions of each other. And now this is where you run to your calculator. So you have, actually, I'm going to rewrite that ln of 0.01 as ln of 10 to the minus 2. Because then what can I do with a minus 2?
Pull it out.
Yeah, you can pull it out. So t is minus 2 natural log of 10 over minus 0.01. It seems strange to have a negative in here because time is obviously going to be positive, but we can have a negative or a negative. So we do get a positive value after all. So 2 natural log of 10 over 0.01. And natural log of 10 is about, well, I'm just going to fill in the value that I know. So it's about 2.3 over 0.01. But dividing by 0.01 is multiplying by 100. So it's supposed to get roughly 460 minutes. Oh, okay. Yeah. So I used a few more decimal a little more accuracy in my notes. So 460.5 minutes. So it takes just shy of 8 hours for the
What is it? Natural log to the negative.
okay, are we good up to here? Okay, yeah, so I just rewrote 0.01 as that. And then, because of the properties of natural logs, if you have that, you can pull the exponent out. So that's what I did there. Okay. I was now remembering, actually it was about, over 5 years ago, when I was cringing over seeing generally a top student using a calculator to figure out how many minutes there are in 8 hours. But I shouldn't have talked back then, because now I see students using a calculator to figure out 2 squared. So there's it. For this one, you should use a calculator, but I think the most egregious of all is someone using a calculator to determine whether 4 was greater than 3, because it had like the comparison operators in it. So we're doomed. All right. This is why I don't set foot in a math zone. Okay. All right. So questions about how we arrived at this? Oh, wait. Oop. Sorry to anybody who's watching, like the people who should have been here today. That's what they get. Okay. Questions? All right. I'll use the remaining time. At least start the next example, which is a significantly different application, at least. Okay. All right, so in this problem, suppose you're investing K dollars per year. So every year you're dumping K dollars into an account, and then and little r is the rate of return. And then S of t is the value of the investment. At the time t, and we'll use years to measure time. Okay. So the goal is for the amount, the value of investment after 40 years to be equal to 1 million. For given K or R, so for example, if you decide to fix the amount K, so you specify a number for K, what does R need to be so that you'll hit this goal? Or the other way around. You know what the rate of return is. What should the amount of your annual investment be to hit that goal? So you can look at the problem from different perspectives. And we assume, okay, just for simplicity, because we're just looking for a ballpark here. We assume continuous compounding also. In lower level math classes, you may have dealt with compound interest. Actually, I'm teaching Math 102 online, so it comes up in there because they should have a business application once in a while. So the differential equation in that case is, so by continuous compounding, you're going to get, the amount by which the value of the investment is going to change per year is going to be the amount that is already in there times the rate of return, so that's R, So that's just from the money sitting there earning that much. But then you take into account how much you're pouring in per year. So that's where the K comes in.
Is that an integral or is?
That is just a plain old capital S. Yeah. Yeah, my integral sign's are a little more vertical. All right, it's not as different as I'd like it to be. Okay, I'll work on that. We've got the whole A versus Q thing all over again. All right.
Well, if you draw them like you said you would, we won't have a problem.
Okay. Oh, I mean that? Okay. So that's what I should have done. Yeah. Y prime is equal to P of T, Y plus. All right. I should figure out how to do that in LaTeX. So I can fix my notes. Okay. So, all right. Time is running short. Now, what kind of equation is this? What? Yeah, it's only a linear equation. This one, because of the presence of K here, well, actually, wait a minute. K is a constant. It is separable. If K was an actual function of T, so the annual investment was varying over time, then it would only be linear and not separable. Okay, so but if we treat this, instead of treating it less more like a separable equation, so if I rewrite it like that, so now this is in that form over there. So we have P of T is equal to R, and Q of T, sorry, minus R, and Q of T is equal to K. All right, so I'm trying to be consistent. So now what you can do is, what is your integrating factor for this problem? This is what you'll be doing on the homework.
You do the integral of P to.
Yes, which is, yeah, so e to the integral of minus r, but that's just e to the minus rt. Okay, so then what you can do is multiply through, well, actually, we'll just jump straight to the solution formula. So S of t is equal to 1 over that, so that's e to the rt, times the integral of your integrating factor, e to the minus rt, times your q, which is k. All right, and then you just have to keep in mind, when you integrate, number one, don't forget the plus c, and also it's still going to be multiplied by the e to the rt. What is the integral of e to the minus rt?
Negative e to the RT.
No.
Wait, no, there.
Negative R. Negative
1
1 over R.
over, yeah, when you're differentiating, you multiply by this. When you're integrating, you divide by it. That's why I'm highlighting it, because that's a very common mistake. So e to the minus rt over the coefficient of your variable t, so minus r. So now you have your general solution to this problem. And then what you would need to do is, give it an initial condition, you can go ahead and solve for c. And in this example, let's suppose that we start out with nothing. S of 0 equals 0. So what you do is, the initial time, you plug that in for t. Your initial value, you plug that in for s. So we need to solve this equation. So s of t is 0 is equal to e to the rt. Well, t is going to be 0. And then we have e to the minus r 0 over minus r plus c for c. And this can be simplified a little bit. All right, I'm just using my last minute. So we need to solve 0 is equal to plus 1, and we have minus k over r plus c. So that gives away the value of c. All right. Is k over r. So now I can put that in to my solution formula over here. So S of t in general is e to the rt, and then k over minus r, e to the minus rt, plus k over r. And the very last thing I'll do that you can scram is factor out the k over r, and I need to distribute e to the rt through here. So I'm going to have minus e to the rt, e to the minus rt, plus e to the rt, simplify, and so this becomes 1, so we have e to the rt minus 1. So that is the general solution for a case where you have no money down investment. So we're playing K per year. So we'll revisit this on Friday, talk about how to solve for different parameters.